Being able to determine the density of gas is an important skill to have. Knowing whether the gas will sink or float determines what collection technique you're going to use in an experiment. Do you hold the container upside down? Do you hold it right side up? Do you need a lid on it or not? It can also pose safety concerns. If you have a gas canister that's leaking, if it's poisonous gas, is it going to rise to the top of the room and you need to get down low to protect yourself, or do you have to do it the other way around? Now I'm sorry, I had a glitch on my iPad and I couldn't upload the density note for some strange reason. So you'll just see a blank page, but we'll just go through all of the examples. Now, since all gases at STP have the same molar volume, remember Avogadro figured this out to be 22.4 liters per mole, but different gases have their own unique molar masses. They're going to have different densities. Now you started calculating densities in grade 9. Density is given to you by the formula D, density, equals the mass in grams over the volume in liters. Now here are a couple of examples. If you're dealing with a density question and you don't know what amount of gas to work with, you can always choose a fake 1 mole sample, figure out the information to plug in for mass and volume, and then that will give you the density. Now the density of a gas doesn't change as long as you stay at constant temperature. So on your note you've got 2 examples. Here we're going to calculate the density of hydrogen gas. If I take a fake 1 mole sample, I know the mass of the gas is going to be equal to the molar mass of the sample. Because the formula of hydrogen gas is H2, then 1 mole of H2 would be 2.02 grams. Now if I have 1 mole of gas at STP, then I know the molar volume is going to be 22.4 liters. So the density of hydrogen gas at STP is going to be 0.0902 grams per liter. If we compare that to another gas, CO2, we can do the same sort of calculations. So the density is going to be equal to the mass of a 1 mole CO2 sample, so 44.01 grams divided by 22.4 liters. That gives me a density of 1.96 grams per liter. Now, since the density of air is 1 gram per liter, this means that hydrogen gas floats, rises upwards, because it's less dense than air. And CO2 sinks because its density is greater than air. Therefore, if I'm making CO2 in a reaction, then I don't need to worry as much about capturing the gas. It's because it's denser than air, it's actually going to stay in my beaker, and I can carry the sample around without a lid. Hydrogen, on the other hand, is the opposite. I need to collect the gas in an upside down container to make sure that it doesn't rise and escape. There are a couple of pages in the old grade 11 textbook. You can find them by the back door on the bookcase. Sometime during this period, read the pages that are listed in your note about the killing lakes. Before you do that though, let's have a look at example 1, calculating the density of a gas that's not at SATP. So example 1 says, what is the density of pure Cl2 gas at 15.2 degrees Celsius and 137.1 kPa? Now it's important to note that the density of a gas will change because the volume can change based on the conditions. So notice in the question it doesn't give us the size of a gas sample. So we'll start by taking a 1 mole sample of gas, and we'll use that to find the information to plug into our density equation. If I have a 1 mole sample of Cl2, its molar mass will be 70.9 grams per mole, and so the mass number I'm going to sub in here is 70.90. We'll keep 4 sig digs on this. Now I need the volume of that 1 mole sample. Now it's not given to me in the question, but it gives me the temperature and the pressure. And because I'm assuming a 1 mole sample, I can use the ideal gas law and solve for the volume. So let's sub in what we know. The pressure is going to be 137.1. I'm solving for the volume. I took a fake 1 mole sample. Let's throw 4 sig digs on that so we can keep a good answer. R equals 8.314. And the temperature is 15.2 degrees Celsius, so converted into Kelvin, that's 288.2. If you rearrange for the volume, our 1 mole sample of chlorine gas will be 17.48 liters. I can now take that volume and solve for the density of the gas sample. Now I think I have more sig digs than the answer that is on your note, but that's because this time I included 4 sig digs in my molar mass.